Okie dokie. So, time to get toward the meat of our discussion on area, because so far it's been rather plebeian. But let's hit some upper level stuff today. Let's talk about dissections. We are going to say that two regions, two polygonal regions, are equivalent by dissection if you can triangulate both regions in such a way that the triangles in the one are congruent to the triangles in the other. In other words, if you can take the one, cut it up into triangles, rearrange the triangles, and get the other, then those regions are equivalent by dissection. Consider, if you will, this region R, that's the red rectangle, and this region R prime, which is a blue parallelogram. Those regions are equivalent by dissection. We're going to say that R is equivalent to R prime. Because I can take, oh, this is going to be fun. I can take these triangles and bring them over here and with a little bit of work and a little bit of luck, create the red rectangle from those pieces. Because I can make the red rectangle from the pieces of the blue parallelogram, the red rectangle is equivalent by dissection to the blue parallelogram. They are what we call scissors congruent. This idea of dissection matters because if we're going to talk about area, it might be useful for us to take regions that we don't know about and make them scissors congruent or equivalent by dissection to other kinds of regions that we do know about. There is a fundamental theorem of dissection theory. Yes, friends, there is a fundamental theorem to dissection theory. Of course there is. And it goes like this. If R and R prime are polygonal regions, and the area of R is equal to the area of R prime, then R is scissors congruent to R prime. It is possible to triangulate R and to triangulate R prime in such a way that the triangles on the one correspond to the triangles on the other, congruent each to the other. This is a fascinating result, particularly because it's not true in 3 dimensions, but that's a whole other story. The usage of this notation is deliberate. It should recall some things from your Intro to Proof class where you talked about equivalence classes. We mean that this is an equivalence relation. We mean that R is equivalent to R for all R, which should be fairly obvious. That's the reflexive property. I can take any region and break it up into triangles. I mean, that's what polygonal means. I can break it up into triangles. So if I can break it up into triangles, I can break it up into triangles. And the correspondence is between each triangle and itself. This is symmetric. If R1 is equivalent to R2, then R2 is equivalent to R1. whatever correspondence takes these triangles to there, we just reverse the bijection from these triangles to those. The third part is a bit more tricky, but it is transitive. This relationship is transitive if R1 is equivalent to R2 and R2 is equivalent to R3, then R1 is equivalent to R3. Now, you're thinking the big sketch of the proof is whatever triangles correspond to these, well, then we'll just let those correspond to those, but that may not be true. This ordering, this decomposition from 2 to 3 may use different triangles than the ones from 1 to 2. But what we do is we break up the R1s and the R2s into sort of very small units, and then we lump together all the 1s, correspond them to 2s, and the 2s to 3s, and we get it that way. It doesn't have to be that whatever triangles we use to break up 2 over here, we use to break up 2 over here. But we can break up the triangles from here and the triangles from here into smaller units, all triangles, and let the 1s match up with the 3s. That's the way that's going to go. Now, why does that matter? Why do I care about that? Well, I care about all that because I would like to talk about this triangle, ABC. It's a generic triangle. No, let's not. Let's renumber. Let's relabel the vertices. This is triangle ABC. What I'd like is to find a quadrilateral, a Saccheri quadrilateral, that is basically, for all intents and purposes, the same. And the reason I want to do that is because it's going to make my hyperbolic geometry study way more easier. Way more easier. So here's what we're going to do. Let's color the triangle. Let's see, can I just color the triangle? No, I gotta restart. Just color the triangle blue, just to keep some things straight. Evidently not the sides, because I evidently can't draw. So here's what we're gonna do. We're gonna find the midpoint of AC. Call that M, and the midpoint of BC, call that N. We can construct a line through MN. We're going to drop perpendiculars to that line, to the line MN. So MN gets constructed, and then we drop perpendiculars to it, hitting at E and D. We drop perpendiculars just like so, midpoint, midpoint. The claim is that ABDE is a Saccheri quad. In fact, ABDE is the Saccheri quad associated with triangle ABC. That's the claim. The two right angles are easy. They're obviously there. The question is, does this end up congruent to that? And the answer is surprisingly simple. The answer is yes. We drop a perpendicular here from C to some point, I don't know, a foot of a perpendicular, maybe that's F. It should be fairly straightforward for you to prove, and you should be able to come to class able to do this. You should be able to prove that triangle AME is congruent to triangle CMF, and that triangle CNF is congruent to triangle BND. And if those triangles are congruent, then those imply that AE is congruent to BD. Just a thought. I think you should be able to finish putting that proof together. It's not terribly difficult. Now, why do I give a rip about Saccheri quadrilaterals? Well, I give a rip about Saccheri quadrilaterals because the area inside the Saccheri quadrilateral is the same as the area inside the triangle. Because this triangle is outside the quad, but this triangle is inside the quad and outside of triangle ABC. Similarly, over here. Furthermore, as will become important in hyperbolic geometry, the defect of triangle ABC is the same as the defect of triangle ABDE because of all the congruent sides and congruent angles going on in these cases. The areas are the same between the red Saccheri quadrilateral and the blue triangle ABC, and the defects are the same. And that will matter. That matters a lot. As a side note, and not a side note of any great importance either, if we were to do the same kind of construction but for a parallelogram, so you take the, I'll go green, take the midpoint of AC and the midpoint of BC, and then you extend ray MN in this direction to some point over here, so that this is congruent to this congruent to this congruent to that. Then the claim is that parallelogram ABGM is the parallelogram associated with triangle ABC. And again, the reason that all matters will become more apparent when we hit hyperbolic stuff. Suffice it to say, it is helpful to know, given a particular triangle of unknown area, if we can turn it into some other shape whose area we might be able to work with better. Okay? Okay. Furthermore, it should be noted that that green parallelogram and this red Saccheri quadrilateral have the same area. And they have the same area because they both have the same area that triangle ABC does. So bear that all in mind. That's a big deal. Hopefully you understand the construction. Hopefully you can prove why ABGM is a parallelogram. Might not be a bad thing to know how to do when we gather. So why is that a Saccheri quadrilateral? Why is this a parallelogram? We'll see you in class.